Welcome back. So, today we will talk about the paleoseismological studies and normal faulting environment. Now, as I told in the beginning and in number of lectures that the fault scarp which you will come across in normal faulting environment will be very much similar. That is the morphology, very much similar to the fault scarps which you will be able to see in compressional tectonic environment. So, what you see here is the a small warp here, and this photograph is from Bulgaria, which shows a very beautiful scarp. This side is comparatively up and this is down, but in case of the normal faulting, this is the hanging wall, this is the footwall here. So, let us see a few examples from the normal faulting environment, and one which I am going to put from Bulgaria, and another is from the along the Irpinian fault in Italy. So, this presentation basically comprises the slides and the data which was supplied to me by the respective authors from this region who are working basically the paleoseismologists. So, let us move ahead and see what best we can learn from how to conduct the paleoseismic studies and what we should look in normal faulting environment. So, this is the scarp in Bulgaria, which is the higher portion here, and then you have the lower part at this stage. This is your footwall and this is your hanging wall. This close up of that, you have a very beautiful scarp. So, if you take in profile across this one, then you will be able to see something like this. Okay. Again, another edge of the fault scarp. So, what we see in the section, so basically we try to, as we have discussed in the technique, that we try to open the section and try to see the old earthquake signatures preserved in the sediment or in the stratigraphy. So, this is a trench, and in techniques also I have discussed this field techniques, that how you open the trench, you take the some part of the scarp and then you get down into the frontal base part or the toe of the scarp, and further in the ground, which is undeformed layers. Okay. And you will try to identify the different units. So, this is the same way it has been done. So, the trench wall has been cleaned properly, the material which has been excavated has been kept out, so that you can move along the wall here on the top, and then you do grading and mapping and all that. Okay. So, fault, as if you look at in the previous slide, so fault runs exactly at the base here. So, this is a very common way of identifying that where exactly will the displacement you will come across. So, mostly because of the erosion of the free face and the deposition, the fault will be seen at this location. So, what you see is the displacement here, and based on the different colors of the layers you can easily identify those things. And then you have a very thick soil layer here, humic rich, organic rich layer is there. So, on the upper portion of the scarp you will have very thin deposit, because this is down faulted, hence you will have a very thicker material or the deposition of the sediments which will take place here. So, mostly you will see in the upper portion you will have thinner thickness of the units will be less, whereas in the down faulted block you will have thicker sediment succession. This is the close up of that. So, you have a fault zone which goes here. So, one fault which reaches right up to this, another one goes and stops somewhere here. Okay. So, the cross cutting relationship has to be taken, and this is the topography of the last event on which the deposition has occurred and resulted into the formation of soil. So, next event, this will be this will break, and this is what we call this will be the event horizon for the next event in future. Now, coming to the one of the beautiful example of normal faulting in Italy, and this work was been carried out by one of my close friend and her group, Daniela Pentosti from INGV Rome, and she supplied this presentation. So, usually I use this for teaching purpose, and I hope that this is going to be a useful presentation to understand the faulting environment basically in extensional tectonic. So, if you want, you can have the details from Journal of Geophysical Research. The paper was published in 1993 by Daniela Pentosti and her group. So, this was the rupture which occurred along the Irpinian fault in 1980, and that earthquake was been named as Irpinian earthquake. Now, one thing which similar thing which we want to do in India also, that we want to map each and every active fault trace on the surface, and then we should have the details. So, this is one way of putting the data in digital form, that when you click this, you will get the all information about the respective faults, when it moved last, and what is the history in terms of the earthquakes on particular fault, and what are all geomorphic features. So, this is all data has been put on GIS platform. So, and available for the users in public domain. So, whosoever required this information for any development or any other project, then they can have this information using that site. So, this was the rupture, and the magnitude was not very high. It was around 6.9, that occurred on 23 November 1980 Irpinian earthquake, and the rupture has been seen here on the surface, and this was the scarp which was formed in that region. So, 1980 rupture was been identified along this fault and different locations. I will show a couple of photographs of this which they have taken, and then finally they decided to undertake paleoseismic studies in one of the best location which provided them the history of the faulting along Irpinian fault. So, this was again the amount of displacement which was been observed after the earthquake, which was measured, and as I was talking in one of the lecture, that the maximum displacement was in the epicentral area, and it dies out on either end. So, this was the location where these are the two locations which have been shown here, which shows maximum displacement during the 1980 Irpinian earthquake. So, this was the scarp, very beautiful clear scarp in Young's deposit, where the surface, this surface and this surface were same before the event, and which got displaced. So, what they did was this the scarp was identified, and this was the best area they filled based on the geomorphic studies that can provide them the signatures of the paleo earthquake if this fault has moved in the past. So, these were the two trenches which have been dug, and I will just talk about that what they found actually in this region. So, they had like the river which flowed through this region got blocked along the fault. So, they observed a sort of an ponding condition here, and a ponding condition will result into the formation of the humus rich soil, and that was one of the point they took into consideration, that if similar event has occurred in the past, similar activity would have occurred. So, blocking of the channel during an earthquake and then further erosion and dissection of the scarp. So, Piano di Pecore was one of the few sites favorable for trenching. So, that what they identified for paleoseismic studies, and these were the trenches which were open, which clearly shows this previous scarp here, and then you have the present one which has been seen here, okay, and the fault runs somewhere over here. So, the close up of that has been shown here. So, trench 1 was located in the middle of the area and exposed the magnificent stratigraphy. So, such stratigraphy if exposed, which you can compare with the footwall. This is the scarp with a very low scarp, but of course very beautiful stratigraphy was exposed along this. So, final trench which they sketched, they found that there are the faults are been identified here, of course, and that will tell you the cross-cutting relationship. Okay. So, as we discussed in one of the lecture, that the normal faulting will not occur along single fault plane, but you will have multiple faults. Now, there are few faults which are not exactly going deeper, but they are the part of the deformation. So, this deformation should also be taken into consideration to identify the ancient earthquakes based on the cross-cutting relationship. The best which you can see here, that this faulting displaced or reached up to this point, but not across this one. So, this indicates the earlier event, and this was which cut the right up to this point was the recent event. Now, based on this, what they identified, that there was a drainage flow in this direction. So, they reconstructed the tectonically controlled warp field sequence at this location. So, they had, like, whenever there will be in co-seismic rupture, okay, then you will have the extensional cracks which are forming here, or the displacement you will be able to see what has been shown here, and that will help you in identifying subsequent events. So, for example, the drainage which was flowing across this area during the fall, just after the faulting, due to the formation of due to the earthquake, formation of the scarp was resulted, and you will have the blocking of this river, and this will result into the filling up. So, this area will acted as a pond, and that what is been shown here, that filling by the lacustrine deposit. So, over the time, the next event will displace this one, okay, and then so on. So, the fault runs somewhere here, the fault plane is here, and the deformation which we see is the of course the secondary one, but should be considered as in co-seismic displacement, or co-seismic, at least the co-seismic event, the deformation which is taking place. So, when there will be next event, then another scarp will form, the same scarp, of course this will show a cumulative displacement, but you will have the displacement which is going and cutting this deposits also. So, similarly, based on that, they were able to pick up at least 5 events, okay. They were able to pick up 5 events, and they have reconstructed the chronology of the events based on the cross-cutting relationship of the faults which they identified in the trench. So, this shows this event 5, okay, where you have the unit 5 has been shown here, and then unit 4 and so on. So, what it shows here is that you have the unit 5 which was displaced, and then further, because of the again the blocking of the channel, deposition of unit 4 which capped the unit 5, the deformed unit 5, and then there was an event here which displaced unit 5 as well as unit 4, that is your event 4 you have, and similarly what has been shown the previous one. Then there was a phase of sedimentation that resulted into the deposition of unit 3 which capped the the displaced unit 4 as well as 5, but the top contact is your unit 4 and then you are coming to unit 3. So, this was the phase of sedimentation. Again next event, that is event 3, the layer 3 was the event horizon which got displaced, and again sedimentation which deposited or capped the unit 3 over here. So, you see no displacement here, but the next event, event 2, again displace the all the units, okay, like unit 5, 4, 3 and 2. So, this was the event horizon. Now, another phase of deposition, that was unit 1, which capped the event which occurred, that is event 2, unit 2, and then finally it displaced, that was event 1 in 1980. So, this has been shown in the next coming slides. Okay, you have event 5, then the phase of deposition, that is pre event 4, and then you have the displacement event 4, then capping of event 3, then event 3 displacing event layer 3, capping by unit 2, and then event 2 displacing unit, and then finally event 1, which displays the most recent event or most recent layer, that is your layer 1. So, this all these units are marking the event horizons which are reflecting the different events, event 1 to event 5. So, this is how you can reconstruct the history of the paleo earthquakes in this region. So, at least from this trench investigation, what you can decipher that on this particular fault, this was not the only earthquake which occurred in 1980, but there were more events. Now, the part comes is of the dating. Okay. So, the two trenches was located less than 100 meter away from trench 1, but exhibits a very different style of deformation. So, again this is an important part which usually we come across, because the fault will have different attitudes, that is the dip and strike also it will change, and it may result into different style of deformation. And also some places, suppose we have the fault trace here like this, okay, and then you have open up. So, this is your scarp here. So, you have like I will just put here, this is your scarp here, and then you have the surface which is coming down here. Okay. And suppose you have opened the trench across this one, okay, and then you are opening the trench somewhere along this one here. Now, the possibilities are there. This is your scarp. The strike of this and this portion is different. So, style of deformation may vary at different location. Another point is, one is you have to take into consideration, one, the strike of the fault change, okay, and then second is your deposition also. So, you may have difference in sediment succession also. So, you may be able to pinpoint the difference in the paleo earthquakes also in such regions. Okay. So, it is always better to have more than one trenches in the close by region, so that we understand that what exactly has happened, to have the complete history, at least up to the stratigraphic section which we have exposed. So, this shows the fault zone very much similar to what we were looking at in the trench in Bulgaria. So, red pins are marking the faulting. So, this is this portion has been displaced here very clearly. So this is your down faulted block and this is your stationary block. So based on this, the another important part which comes is after identifying the event horizon, then based on the cross-cutting relationship between different layers or the sedimentary units, then the task is to identify the location of the samples, okay, for dating. So this is what it has been shown here by triangles over here. These are the location of different samples which were been collected, and the dating is basically done using the C14 carbon 14 dating has been done here. So charcoal samples, and since this area was under the state of lacustrine environment was prevailing after the faulting of each event, then this portion showed good amount of the charcoal or the carbon content in the different layers. So you have these ages are all showing the carbon ages, and the samples were been collected. Of course, you may not come across the samples or the charcoal in each layer. So wherever you are getting, but you have to target few layers or few units which are important to talk in the history of the faulting on particular fault. So these are all ages. Based on this, the reconstruction was been done, that when such earthquake, for example, if you take this sample, okay, and this sample, then at least to some extent, if you say that this was displaced, so you can say that the event was between this and this. Okay, so after the deposition of B unit and before the deposition of A unit, if you are targeting this event here. So that we will discuss more when we are talking or discussing of the faulting environment in compressional tectonic environment and all that. Now further, so trench 3, and then so several trenches were been done, and based on that and the ages which were been compiled, so this shows a very beautiful fault here again, displacing the blackish unit. So several ages were been obtained, and based on the radiocarbon ages they were calibrated, and then you have the ages in before present. So paleoearthquake of the Irpinian fault, this what they identified, and based on this different events. Event 1, okay, which has the minimum age definitely was 1980, okay, and then event 2, which was during this period or between this two, and event 3 between these two ages, and so on. Okay. So based on this, the average recurrence which was been identified was around 2000 years between the respective events, and the average slip per event was almost around half a meter. Slip rate which was been calculated per year, and taking into consideration the age and the slip per unit, you can calculate the slip rate. So elapsed time is around 22 years, and the magnitude which was been picked up for each event, and also which was the magnitude of 1980 earthquake. This was magnitude 6.9. So surface faulting earthquakes on Irpinian fault, this is what has been given. So you have the paleo earthquake events, the time scale. So this is the elapsed time between the two events, that is your recurrence between the two events, and if you see clearly, it is not exactly the same. Okay, but you have in between, you have the pockets of smaller earthquakes here, like event 2 and all that. Okay. So this is how you can undertake the paleoseismic studies in different environment. Okay, so this was from Irpinian fault, looking at the normal faulting environment. So I'll stop here, and we'll continue in the next lecture. We'll see more on what we have to learn from the compressional tectonic environment. Thank you so much.